And our plan today is that we are discussing chapter 4, and in chapter 4 we want to talk about what we call generating functions. We will discuss generating functions. Now, I'll send you the notes for this chapter. Already prepared them, so don't worry. After the lecture, I'll send you the notes. So these functions are called generating functions because they do generate something. And the generating functions are of two types. We shall talk about two types of generating functions. We have what we call the moment generating functions, and then the second type is the probability generating functions. We have moment generating functions and probability generating functions. So let's switch to the moment generating function. Let's switch to the moment generating functions now. Before we define the moment generating function, we need to remind ourselves of the definition of expectation. The definition of expectation for a function g of x. We say that the expectation of g of x, if g of x is a discrete, then it is the same as sum this function g of x then times the probability of x is x. So the expected value of the exponential function etx is essentially important in this section. So let's define the moment generating function. The moment generating function is denoted by m. It is a function of t, and x is the random variable. So the moment generating function of the random variable x is denoted by m subscript capital X, then t of the random variable, and it is defined as the expectation of this exponential function. The moment generating function is defined as expectation of this exponential function. It is e of tx. Now, how do we get this expectation? If x is a continuous random variable, then the moment generating function is said to exist, because now this expectation for continuous we integrate to get expectation. So we integrate from the lower limit up to the upper limit, then the function is e of tx, then times f of x. So if this integral exists, then the moment generating function is also said to exist. The moment generating function in this case is said to exist. And if x is discrete, then this is how we generate the moment generating function. This is how we get the expectation of the exponential function. So precisely, the moment generating function is defined as expectation of this exponential function. This is e to power t, then x. Remember, the x here is capital and the x here is lowercase, because when we evaluate, we are looking at outcomes. Before we evaluate, we are looking at random variables, and random variables are represented by capital letters. So precisely, the moment generating function of random variable x is defined as the expectation of the exponential function, and this expectation is computed like this if x is a continuous random variable, and it is computed like this if x is a continuous random variable. So that is the definition of the moment generating function. Is it clear, Bosco? Is the definition clear?
Yes.
Okay.
Yes, sir.
Good. We can proceed with the properties now. We can proceed to properties, the properties of moment generating functions. Rachel, you had gone out, or she's even still struggling to, she's struggling to log in. Okay, Rachel, you had moved out. What's your problem? You are on and off.
Just my network is now disturbing me.
Sorry, I told you to get stable network. Probably at campus there is.
But here it is kind of stable now.
Okay, now let me take you back to the previous slide where I defined the moment generating function. Did you get this definition? In this slide, we are defining the moment generating function. And then in the next slide, we are talking about properties of moment generating function. And I said the moment generating function of a random variable x is denoted by mxt, and it is defined by the expectation of this exponential function. This is e power something, expectation of the exponential function. And we said if if the random variable x is continuous, then the moment generating function is computed like this, because this is how we compute the expectation for continuous. And if x is discrete, we compute it like that. Are we together on the definition of moment generating function, yes. Rachel?
Oh, good morning. How are you, Emma?
Yes, sir.
Okay. So we proceed to properties of moment generating function. The
Yeah,
first
I found it
property
and I
is
found
that
I left my phone
the moment
and
generating
came it was
function
red, so I
exists
couldn't
at
call
a
you back.
point t equal to 0. The moment generating function exists at a point t equal to 0, and its value is given by, when we evaluate it at t
All
equal
right,
to
it's okay.
0, it is
All right,
expectation
man.
1, and it will be 1. Where do
Yeah,
we
thank
get
you.
this? If
Thank
we
you.
go back here, you see by definition, this is the moment generating function. So if t is equal to 0, then this is going to be expectation of 0. Where there is t put 0, you get expectation of 0, and anything to power 0 is 1. So it means that the moment generating function at t equal to 0 exists, and its value is 1. So this is the first property. The second property is that suppose that the moment generating function of x exists in an interval containing 0. So the moment generating function exists, then the derivative of mxt. So when we differentiate it, once we get the moment generating function, we can differentiate it to get the first derivative. The first derivative also exists. The first derivative also exists. And under suitable conditions, it is possible to change the order of expectation to differentials. So we get, once we differentiate the moment generating function at t equal to 0, because to differentiate is a linear operator, so to differentiate the moment generating function is the same as differentiating this exponential expectation of the exponential function, which is the same as expectation. We can differentiate what is inside. So when we differentiate this, when we differentiate e to power tx, we get x e to power tx, because when you differentiate here, then you multiply here. So when you differentiate here, you get x. Then you pre-multiply it, it is here. So you get that. And when we evaluate at t equal to 0, when t equal to 0, e to power 0 is 1. So this one gives us expectation of x. So this shows us how the moment generating function generates, how it generates the expectation. So this expectation is the first moment, call it the first moment, Hence, that's why this chapter generates its name, moment generating function, because they generate something. And the first thing they are generating here is the expectation. So these are two properties. The first property, it exists at a point t equal to 0 and its value is given by that. The second property is that if we differentiate it with respect to t and evaluate it at t equal to 0, we get the expectation of x. And those are the only two properties. More generally, if the moment generating function of x exists for all values of t in an interval containing 0, then it is possible to differentiate the moment generating function a number of times. We can just keep on differentiating. Are we together on these properties, members? Members, are we together on these properties? Members, are we together on these properties? Let me get feedback from you members. Are we all together on these properties?
Yes, sir.
Yes, sir.
Okay. Okay. Now, we are saying that generally we can differentiate several times. Generally, we can differentiate several times. So the nth derivative, it will give us that, and it will give us the nth derivative evaluated at t equal to 0 will give us. So when we want expectation of x squared, we will differentiate the second time. If we want expectation of x cubed, we differentiate the third time. We want expectation of, and so on and so forth. So in particular, expectation of when we differentiate the first time we evaluate at 0, we get this. When we differentiate the second time evaluate at 0, we get expectation of x squared. And once we have expectation of x squared and expectation of x, we can always get the variance. We are used to this. We can get the variance. So that's the variance is given by that. So you see, using moment generating functions, it simplifies life, because previously we would find expectation of x alone, find expectation of x squared alone, then get the variance. But now we just get one function called the moment generating function. Then this moment generating function generates for us the expectation. Generates for us the moments. The first moment is expectation of x. The second moment is this. And once we have the first and second moment, we can compute the variance. We can compute the variance. Now, I want to show you some example. And it is not on the slide. Of course, we are going to find the moment generating functions for all the distributions we discussed in chapter 3. Starting with discrete distributions, we shall find the moment generating function of a Bernoulli distribution, the moment generating function of a Poisson distribution, the moment generating function of a geometric distribution. Those are discrete. Then under continuous, yesterday we discussed the two examples of continuous distributions. But for the two examples, we shall not find the moment generating function of a normal distribution. That one is, we shall not find it. We shall only find the moment generating function of one continuous distribution, which we call the exponential distribution. So let me try to find for you examples here. Let me try to find for you examples here, if I can. So you see, this is what we've been discussing. So this is the example, the first example. Let x be a random variable with a probability density function So which type of random variable is this? Is it continuous or discrete?
Right. Right.
Rachel,
Yes, sir.
which random variable is this? Is it discrete or continuous?
Continuous.
It is
Continuous.
continuous. And you see, it resembles the exponential distribution
Right.
that yesterday.
Right.
It
Yeah,
resembles,
but I'm missing you missing there. A little bit confusing.
I think Bosco should mute. Bosco, try to mute. You have noise in your background. Try to mute your microphone, and you can only unmute if you want to say something so that your noise doesn't affect us. Okay, thank you. So we agree that this is a continuous random variable. So we want to find its moment generating function. So here we go. Here we go. Here we go. Here we go. The moment generating function is, by definition, expectation of the exponential function ETX. So since it is continuous, we can integrate from 0 up to infinity because that is the interval over which it is defined. 0, x greater than 0. So we have a starting point 0, but we don't know where x is ending. So we integrate from 0 up to infinity of t of ETX. So we put ETX for this, then we multiply by f of x, but f of x is that. So that one is the same as bases are the same. So we combine the powers. So we get t minus x into that. And this integral is finite if and only if t is less than that. So when we integrate, when we evaluate this integral, we get this as the moment generating function. We get this as the moment generating function. And let me show you the working. Here there is no working, but can everybody access your WhatsApp? Can you keep on Zoom and access WhatsApp? Is it possible? Oh.
Yes, it is possible.
Okay, so let me post this example, but I think I can even push it here.
So
I can even push it here because we don't have a general group. I can push it here. Let me try to push here together with the working, together with the working. Let me push it here. Let me push it on my screen. Let me push it on my screen. Let me try to push it on my screen. Let me try to push it. Okay. I can't succeed. Can I succeed? I seem not to. Okay. Okay. Let me give it to Rachel. Okay, I've failed to push it on the screen, but I've posted it on WhatsApp. It shows the full working And what I wanted to show you, there's something we need to correct here. This should be negative, such that on putting in limits, it is e of negative infinity, which is 0. It is e of negative infinity, which is 0. It is e of negative infinity, which is 0. Yeah, so that's what we get. Is it clear, members?
Yes, sir. We've received it.
In the WhatsApp, have you seen the working in the WhatsApp?
Yes, sir.
Okay, now in the WhatsApp, I try to integrate, and on the integration, I try to put exponential of negative. That's why in brackets, I have 1 minus t. And when to integrate, we differentiate the power of the exponent, then we divide. So it will be negative 1 over 1 minus t, then e to the power negative into 1 minus t, then the limits are 0 up to infinity. Rachel, are we together? Rachel?
Yes, sir.
So 0 up to infinity.
Yes, sir. We are together.
Then when I put in the upper limit, it is infinity. So it will become e of infinity minus e of 0. Now, e of infinity is 0. E of negative infinity is 0. But e of positive infinity is not 0. So that's why I wanted us to create that negative there. So e of negative infinity is 0. Then minus e of 0, which is 1. So 0 minus 1 is negative 1. So it gives us that as the moment generating function. Now, in the second example, okay, let me not talk about this because I never discussed with you the discrete distribution. I never discussed with you the discrete distribution. I never discussed with you the discrete distribution. Okay, let's go back to where we were on the properties, and then we try to continue to, so these are the properties. They are basically two properties. One, we say the moment generating function exists in an interval containing 0, and its value at t equal to 0 is given by expectation. I mean, it is given, yeah, it is given by 1. 2, we can differentiate to get the moments. Get the moments, we have to differentiate. Now, more examples. Let's start with the Bernoulli distribution. Members, do we remember the Bernoulli distribution?
Yes, sir.
What is
remember.
what did we say is the expectation of the Bernoulli distribution?
It is P.
Remember? Yeah, P, good.
Expectation of the Bernoulli is P.
And the variance?
PQ.
PQ.
The variance is PQ, I mean,
Okay.
sorry.
Okay, good. So let X be a Bernoulli random variable with parameter P. P is the probability of success. The moment generating function is derived as follows. So by definition, moment generating function is the expectation of this exponential function. So it means we know that this Bernoulli it has only 2 outcomes. Oh, I wish I had written something down. Yeah, so this Bernoulli has 2 outcomes. It is 0 and 1. It has outcomes 0 and 1. So to get it, we take the sum. I don't know why I didn't do the summing. I am okay. I don't know whether members can get it. If you can try to write down. Let me see. Let me see. Let me try to get my rough paper. I try to do for you something. I wish my camera could. Yeah, so let me allow myself to share. Let me allow. Okay. Yeah.
Recording in progress. Recording in progress. Recording in progress. Recording in progress.
Let me try to. I am connecting my phone. Ask to start. Oh. No, I should see. Okay, let me just write it. Then, as usual, I post it on WhatsApp. I'll post it on WhatsApp. So it is the Bernoulli is X. It has only outcomes 0 and 1. P of X is X. So when X is 0, okay, it is from the binomial Bnx, which is n combination X, then P to power X Q n minus X, then X is 0, 1, 2, up to n. So when n is 0, P to power, when X is 0, P to power that. So this is 1 minus 0, so this is Q. And when this is P, this is P. So it means that the moment generating function of the Bernoulli is going to be expectation of ETX. Yeah, but this is, since this is discrete, we sum from X is 0 up to 1 of ETX, then P of X is X. But when X is 0, this is going to be E of 0 times Q. When X is 0, it is E of 0 times Q, plus when X is 1, this is E of T, because X is 1, then times P. So that's why the moment generating function becomes, because E of 0 is 1, it becomes Q plus P ET. So that's why we get that as the moment generating function. There is one step that is missing here, which I'm trying to work out, and I share, which I'm trying to work out, and I share with us. There is one step missing, which I'm trying to work out, and I share with us here, and here we are. Here we are with this step. Here we are. Here we are with this step. And let me try to see if I can have it. Okay. Let me, Rachel, I've given it to you on WhatsApp. Again, I have issues with my Bluetooth. So I've given you the working on WhatsApp. Rachel, try to access WhatsApp. I think you'll explain to Bosco. I've sent you the working on WhatsApp, Rachel. Have you seen it? Rachel?
Yes, I've seen it.
Okay, so that is the working. That is the working. The table gives the okay, yeah, this is where we are. And the table gives the probability mass function of a Bernoulli distribution. It has only two outcomes because we said it is a special case of the binomial distribution. So it has only two outcomes, 0 and 1. And from the binomial distribution below, when x is 0, then 1 combination 0 is 1, p to power 0 is 1, then q to power 1 minus 2. So we get q. When x is 1, we get p. So when we take the sum, the expectation, moment generating function is expectation of that, but that expectation is the same as summing from x is 0 up to 1 because those are the only outcomes we have. Then e of tx, then p of x. So when x is 0, we have e to power 0. Where there is x, we put 0. E to power 0, then times q plus. When x is 1, it is e to power. Where there is x, you put 1. So we get e to power t, then p. So e to power 0 is 1. That's why we get q, then plus. So that is the moment. That's why we get this. So we can now go back to Zoom. Rachel, you can now go back to Zoom. That's where we get that the moment generating function is q plus PET. That's why we get that the moment generating function is q plus TET. That's why we get that the moment generating function is given by this. Now, having gotten the moment generating function, we can differentiate. When you differentiate with respect to t, the q is a constant, it will go to 0. So when you differentiate PET, you get PET. And when you evaluate the first derivative at t equal to 0, you get the first moment. When t is 0, this is PE to power 0, which gives us P. And that one means that the expectation is indeed P, like we saw previously, and like Rachel reminded us. Now, differentiate it the second time. When you differentiate it for the second time, you get, when you differentiate it for the second time, you get still the same thing. When you evaluate, you get P. So expectation of x squared is P. So we use this expression for variance. Expectation of x squared is P minus C, P minus P squared here. So it is P into 1 minus P, which is PQ. So you see, we can just generate the moment generating function, then the rest can be extracted from it directly. So this is the moment generating function for the Bernoulli and how we use it to generate the expectations. Are we together, members?
Yes, sir. It is okay.
Yes.
Rachel, are we together? Rachel?
Yes, sir.
Okay, now I'm going to
Yes,
generate
sir, we
another
are
code.
together.
Yes, I'm saying let me generate for you another code so that we proceed for like another 30 minutes because my time is up. My Zoom gives me a minimum of 40 minutes. My Zoom gives me a minimum of 40 minutes, after which it switches me off. So let me end here. Then I generate another code and I send it to you on WhatsApp so that we proceed. Are we together?
Okay, sir.